Hello everyone, welcome to lecture 40 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on applications of composite for near field superlens. We have discussed the basic composite near field superlens in the previous lecture. So in this lecture we will look into the potential applications of composite near field superlens. What are the limitations of this near field superlens in the area of far field imaging, and then we will look into far field imaging with super resolution. There also we will discuss limitations of far field superlens, and then we will come to optical hyperlens. Okay. Then we move on to discussing challenges and improvements in cylindrical hyperlenses. We will consider plasmonic hyperlenses, which are planar hyperlenses, and then we will also discuss stacked nanorod lenses. So let us first focus on potential applications of composite near field superlens. So random metal dielectric composite films have shown great promise for creating versatile and wavelength controllable near field superlenses, right. So this tunability is key for applications such as biosensing, spectroscopy, sub-wavelength imaging and nanolithography. So the first application we will discuss today will be surface enhanced remote biosensing. So surface enhanced Raman scattering, that is basically SERS, can be used for biomolecules. Okay. So in the conventional SERS, that basically requires the molecules to be directly on the metal surface to benefit from the field enhancement. Okay. Now the metal surface that has got nanoscale roughness act as small nanoscatterers, and they can give rise to electric hotspots. They can basically enhance the Raman scattering effect because the local intensity of the electric field gets amplified several times. However, in this particular case the molecules basically come in direct contact with the metal. So that has got the risk of undesired modifications such as charge transfer or denaturing. Okay. So that basically results in the search spectra representing signatures of metal molecule complexes, not only just of the pure molecule. So this is typically the search setup. Okay, you don't have this part. So this is where you can use this near field superlens for search sensing. We will look into this in more details here. Okay. So this is the first application we will be discussing today, surface enhanced remote biosensing. So the search for biomolecules can be done using this kind of a setup, where you are basically using a composite near field superlens based approach, right. So this near field superlens basically images a search active substrate. So this is where your substrate is. So this basically allows, this superlens basically allows projection of the high local fields onto the other side of the lens, where you can put the biomolecules. Okay. So that is how you can see that the biomolecules are basically placed far away from the metal surface, right. So this particular method has got two advantages. First of all, preservation of the molecules. That means in this case the biomolecules are not coming in the direct contact of the metal, so you can prevent any undesired modification, and also you can ensure the measured spectra are basically coming only from the biomolecules, right. And then you can also have tunability in such a system. Okay. So here is your lens, here is the host medium. So this overall thing basically works as near field superlens. So on the other side you say you are basically putting some kind of medium with biomolecules, and this is where you can get the image of the search substrate. So this is a glass prism which is having this kind of reflection, and some portion is basically getting attached here. So this is basically a metallic substrate, which is typically a search substrate that people use. Now what you get here in terms of tunability, because use of this kind of tunable near field super lens, as we discussed in the previous lecture, that you can change the volume fraction of the metal and can get this super lens work at a desired frequency, right. So, it is much more convenient than a pure silver lens, because that silver lens works only at a particular wavelength, that is in the UV range. Okay. So, this is especially becoming important since semi-continuous films are more effective for ACRS at longer wavelength, which a pure silver film or silver lens cannot achieve. Now, the second application would be non-invasive intra-object imaging. Okay. Now, the setup is shown here for non-contact biomolecule probing, okay, using a composite near field super lens. Okay. So, here we are basically seeing the application of this metal dielectric near field super lens in biomedicine. Now, what are the challenge in biomedicine, or you can say biomedical imaging? You basically need to probe the internal structures of intact cells or spores with sub-wavelength resolution. Okay. So, normally what you do NSOM, that is near field scanning optical microscopy. Okay. So, NSOM cannot achieve sub-wavelength resolution, but it basically requires the fiber optic tip to be within very few nanometers of the object that is getting probed. So, what is the limitation of this approach? This basically makes it impossible to probe inside a intact cell or biological objects without basically damaging or destroying those. Okay. Now, if you use this kind of metal dielectric near field super lens for biomedicine, what happens? You can use this lens solution for non-invasive imaging. So, how it works? You basically can use this super lens that can create a non-invasive imaging system, right. So, this super lens can basically project the image of the bio object onto the other, So, this is the intact bio object in a fluidic channel. This super lens can basically give you the image of this actual object here, okay, on the other side, and then you can bring a NSOM tip to scan that image remotely without ever physically touching the actual object. Okay. So, this technique basically allows for observation of the internal structures in intact biological samples, which is very crucial for biomedical analysis and also detection of the biomedical agents. Now, the third application is in the area of nanofabrication. Okay. So, here you can see nanoscale optical manufacturing. We are considering nanoscale lithography, right, where tunable near field super lens can be used. Okay. So, by using an appropriately designed composite tunable near field super lens instead of using a single material silver slab, manufacturers can use a variety of available laser sources, because this is tunable. Okay. So, this basically makes the nanofabrication process more versatile, and it becomes less expensive as well. Okay. So, as you can see here, because you have this tunable near field super lens that can project the image of a mask which is placed here, okay, with spatial resolution which are far below the diffraction limit onto this photoresist layer which is deposited on a substrate. Okay. Now, because this lens is tunable, you can use different lasers, okay, and you expose radiation from the top, and that images can be formed here. So, you basically can get a laser based nano manufacturing with unprecedented precision. Now, what are the limitations of this near field super lens? Okay. We could see that they are limited in the field of far field imaging, because all the applications we have seen till now, that near field super lens, as also the name suggests, It is limited to the near field zone, basically restricting their use in applications like direct optical imaging with camera or human eye, which are basically far field imaging, right. So, while a perfect lens can theoretically provide far field super resolution, but that is currently not possible due to the inherent losses that exist in the negative index metamaterials. Okay. So, we have discussed this also, because you need material to make those lenses and they are not lossless. Okay. So, the following thing addresses the solution to the problem. So, you can achieve far field you can achieve far field sub-wavelength resolution without using the negative index material. So, how do you do that? So, we are now looking into the mechanism of this far field superlensing. So, one method to overcome the diffraction limit in the far field is to convert enhanced evanescent waves from the near field superlens to propagating wave. Okay. So, you can actually achieve this by adding a periodic sub-wavelength grating to the outer surface of the silver superlens, which will basically act as a coupling element. Now, the grating's periodic configuration will facilitate the conversion of some evanescent modes into propagating modes. So, allowing them to basically travel in the far field, and that you can use for imaging. So, now let us look into this particular topic in little bit more details, that far field imaging with super resolution. So, figure 4 shows experimental demonstration of far field imaging with super resolution. So, A shows the schematic of the far field super lens and its adaptation in a conventional microscope. You can see far field super lens over here. Okay, this is how it looks like. Okay, so here is the SEM image of the nano slit pair object. Okay, so normally if you do with a regular optical microscope, you will see you are not able to detect the two slots or the nano slot clearly, because they are diffraction limited. But when you go for FSL images, that means far field super lens images, you see you are able to get this sub-wavelength details, right. So, here are some specification of this particular far field super lens. So, they have used a properly designed sub-wavelength grating that was basically added to a 35 nanometer thick silver super lens. Okay. And the system basically operates at the surface plus bond frequency of silver polymer interface, that is 377 nanometer, and this has achieved, or this has enabled to achieve the far field image of a pair of 50 nanometer wide nano slits, which are basically separated by a 70 nanometer gap. So, you can see these values are much sub wavelength as compared to the wavelength involved here. So, without this far field super lens, you can see that the conventional microscope basically fails to resolve. However, with that you can actually, with the far field super lens, you can basically resolve. Okay. So, what is the advantage over near field microscopy? In far field super lens, that basically projects the sub wavelength details into far field. So, that allows for simultaneous image capture, and it basically avoids the slow point by point scanning that is needed in the near field scanning optical microscopy. Now, this also comes with some limitation. So, the limitations of far field super lens are that the specimen must still be placed very close to the super lens substrate to prevent the evanescent waves from decaying before they are basically converted into propagating waves by the grating. So, another important aspect is that the one dimensional grating only converts evanescent modes along a single direction. So, you are basically losing some of the information. So, that limits the system to resolving sub-wavelength features of one dimensional objects only, right. So, this basically works only for 1D objects, that is like slit pair. So, when you go for higher dimensional systems, this 1D grating is not going to work, right. So, there is basically an inherent limit to the range of the evanescent wave vectors that can be converted. Okay. So, the system can only basically retrieve waves with transverse vectors which are between nk naught and nk naught plus kg. So, n here is the refractive index of the surrounding material and kg is basically the grating wave vector. Now, this limitation basically restricts the best achievable resolution. So, to resolve a wider range of features, more complex methods such as higher order coupling elements will be needed. Now, let us look into the methods of doing far field imaging with super resolution. Okay. So, you can take help of optical hyperlens which are good at converting evanescent to propagating waves. So, what is the concept here? Optical hyperlens is basically a alternative to grating based superlens that was used for far field superlensing. So, a hyperlens is basically a metamaterial that can convert an object's evanescent waves into propagating waves in the far field. So, instead of using a periodic grating for coupling, a hyperlens uses a unique cylindrical geometry that gradually reduces the transverse wave vector of the evanescent waves until they fall below the free space light wave vector, and this basically transforms them into propagating wave that can be collected in the far field using conventional optical devices, right. So, this is one example of the magnification and beaming effect that you see in a superlens. So, these are the two objects which are in sub-wavelength spacing that can be magnified, okay, and then you can come out of this sub-wavelength domain because of these magnified objects, okay, and these are created by alternating metal dielectric layers. So, we can look into the design principle in more details in this particular slide. So, here you see a hyperlens is a cylindrical or spherical metamaterial that is made of alternating metal and dielectric layers, as you can see here. Okay. So, these layers are basically arranged concentrically. So, these are basically concentrically repeated layers. Okay. So, you basically need to make sure that the two effective permittivities have opposite signs. Okay. So, the condition for the hyperlens is such that the radial permittivity will be negative and the tangential permittivity will be positive, that is epsilon r will be negative and epsilon theta will be positive. Now, this condition basically creates a hyperbolic isofrequency curve. So, that means you have a hyperlens which has got some unique properties. Now, when you have hyperbola as your isofrequency curve, what is the exciting thing there? You can actually achieve arbitrarily large wave vector, okay, because the hyperbolic surface will allow wave vector of any size. So, if your wave vector is very large, your wavelength can be very small. That means it enables the collection of sub wavelength information. And next thing is that the pointing vectors of the Fourier components basically align radially. So, you will get a beam like outward radiation. So, how you can use that? You can use this feature for magnification. That means the hyperlens basically magnifies the image of a sub-wavelength object. Okay. So, where the magnification is basically obtained as the outer radius by the inner radius of the hyperlens. So, this magnification allows the sub-wavelength features to be enlarged and observed using conventional optical microscope. So, if you zoom it and make those features large enough so that they no longer remain sub-wavelength, then they can be picked up by the normal optical devices, right. So, here is one example of hyperlens being used for this kind of application. So, this is a hyperlens demonstrated by the Berkeley group in 2007. So, the structure here is basically a half cylinder with quartz substrate, Okay, now this half cylinder has got 16 alternating layers of silver and alumina, each being 35 nanometer thick. Okay, and what is the pattern? You can see some nanoscale chrome patterns on the inner substrate, and then this hyperlens operates at a UV wavelength of 365 nanometer, and you can see that this feature is enhanced because of this hyperlens by almost 2.3 times. Okay, and the sub diffraction resolution that can be achieved was around 130 nanometer. Okay, so you can successfully plot, get this on pattern imaged using this kind of concept, because after it is done, you can put a conventional lens and then a of the optical microscope, and then you can create the far field image plane, and you can see this beautiful on pattern as an image. Okay. So, what is happening? The sub wavelength pattern is basically first enlarged using hyperlens, and once it is large enough, it is picked up by conventional lenses, and then you can use your traditional imaging to image this, right. So, what are the potential improvements? So, if you use a spherical geometry instead of this cylindrical one, you could improve the performance further by doing uniform magnification and faithfully restoring the object's image on the outer surface, right. So, there are some challenges and issues with these cylindrical hyperlenses. The first thing is that there are strong reflections at the outer and the inner surfaces that basically reduce the throughput, and because it requires cylindrical symmetry, it is not that easy to fabricate, and it also limits the object placement. So, what are the improvements people can do in this aspect? You can think of solutions with transformation optics. You can think of non-periodic layer thickness, okay, that can give better performance. You can also think about impedance matching via local electromagnetic control, and you can also come up with a proposal for planar hyperlens using the transformation optics, which can convert the evanescent waves into propagating mode, but with a flat geometry. So, that would basically allow integration, direct integration with the conventional microscopes, and they will have the potential for biological imaging of cells, viruses, and even DNA, right. So, next we look into plasmonic hyperlens. These are basically planar hyperlenses and optical fiber like systems, right. So, the device here, as you can see, is basically a concentric polymer rings, okay, on gold surface. So, this is the gold surface, and then you have polymer rings like this, okay. So, what is the operational mechanism here? That opposite dispersion slopes at gold polymer and the gold air interface, okay, that allows to form the hyperlens or the superlens effect, okay. So, you can see in this particular figure, which is basically plotting the omega by k, okay, at the gold vacuum and gold PMMA interface, okay. So, here you can see the frequencies been marked, okay. So, PMMA has basically got negative refractive index, okay, as perceived by the plasmons, where the gold vacuum interface basically looks like a medium with positive refractive index. Now, this particular thing, you are having a laser illumination at 500 nanometer wavelength, and then you have this phase matching structure. So, here the plasmons are basically getting generated by this phase matching structure. When illuminated, this structure will basically illuminate the samples which are basically positioned at the center of this superlens. So, this is basically your magnifying superlens, okay, and the lateral distance between the images that are produced by this alternating layers of materials of positive and negative refractive index basically grows the distance. So, the separation will basically grow with the distance along the radius, and they will be now here. So, these are called the super images of these two samples, and that can be picked up by a regular microscope, right. So, this is basically a demonstration of polymer dots which were imaged, okay, and they could achieve sub-wavelength resolution of 70 nanometer. Another application was shown using stacked nanorod. So, these are basically metallic nanolens which are made with chains of silver nanorod. So, this is a different approach because here the lens is basically made of stacked silver nanorod, as you can see. So, this nanorod chains can support weakly damped plasmon resonances, and they can transfer. So, this is the object plane, this is the image plane. So, they can basically transfer images from one end to another in a pixel to pixel fashion, similar to the conventional fiber image waveguides, right. So, the super resolution is basically coming from this fact that unlike fiber bundles where each pixel is basically diffraction limited, here each nanorod chain can capture and transmit the local features with a size of only say tens of nanometers, and they can provide the sub-wavelength resolution, okay. And color imaging is also possible because the nanorod chains are designed, or they can be designed to support multiple plasmon resonance modes, something like RGB principle, okay. So, this particular figure shows the spectral dependence of the plasmon resonance modes as a function of the rod length, okay. So, these are the resonance wavelength, this is the resonant frequency, this is the fundamental one, and then you can get the second, third and the other resonance modes here, okay. So, this tells you that you are getting multiple wavelengths simultaneously. So, you can get the magnification by using tapered nanorod arrays that can be used for magnifying the images, and that allows the resolution to be large enough for observation using the conventional optics, right. So, with that we conclude this lecture, and we will start discussing about hyperbolic metamaterials and super resolution hyperlens imaging in the upcoming lecture. So, if you have got any queries regarding this, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.